I get to talk about a very important point in transformer differential protection, which is the transformer vector group compensation in numerical relays. I would discuss the following points: how to read the transformer vector group, why there are different transformer vector groups, and we would have an example of DYN3 vector group, the transformer differential protection system, how to derive the vector group compensation matrix, the transformer differential protection stability condition, and finally we would have an application on the cell 487E transformer differential protection relay using the CMC 356 test kit. The three-phase transformer windings can be connected several ways, and based on the windings connection, the vector group of the transformer is determined. Now let's see how to read and understand the transformer vector group. We have an example of DYN3 transformer. This vector group consists of three parts. The first part is a symbol indicates the primary winding connection, which is delta connection. The second part are symbols indicates the secondary winding connection, which is a star with neutral connection. The third part is a number indicates the phase displacement of the secondary winding with reference to the primary winding. Normally this number is multiplied by 30 degrees, and the resultant angle is the phase shift between the line current of the primary winding and the line current of the secondary winding. Here in our example, the secondary winding line current lags the primary winding line current by 90 degrees. Great. Actually, the different transformer vector groups are used in many cases and for different purposes, as removing the odd harmonics drawn by the nonlinear loads or the magnetizing currents, providing a closed path for the third harmonics and inhibit its appearance at the primary lines, and this could be achieved by using the delta windings, providing a path for the ground current to indicate the ground faults, and this could be achieved by using the star-earthed windings. Also, the determination of the transformer vector group is very important for the following reasons: calculating the transformer differential protection settings, connecting two or more transformers in parallel in order to avoid the large circulating current flow between the transformers. Now let's see how the DYN3 transformer windings are connected. First of all, we will draw the phasor diagram for both primary and secondary individual windings. Although the primary and secondary phase currents are in phase or out of phase based on the transformer polarity, either subtractive or additive, and our transformer polarity is subtractive. But due to the transformer vector group DYN3, which means that the secondary line current would lag the primary line current by 90 degrees, then this would be the new phasor diagram for the secondary side. Now let's draw the secondary star windings on the phasor diagram. Also draw the primary delta windings on the phasor diagram. We would determine the phases of the delta side where each phase is parallel to the corresponding phase in the star side. So this would be the delta connection. Let's say that the terminals A1, B1, C1 in the star side are connected together to form the star neutral. What about the delta side? The direction of the delta winding terminals would match the star winding terminals, so this would be the delta terminals. It's the time to connect the transformer windings in order to get the DYN3 vector group. For the secondary side, A1, B1, C1 will be connected together, and A2, B2, C2 will be connected to the transformer bushings. For the primary delta side, B1 is connected to C2, then connected to the R phase bushing. C1 with A2 connected to Y phase bushing. A1 with B2 connected to phase B bushing. Great.